Okay. Hello, welcome to the Software Controls Workshop of the OSU Underwater Robotics team. My name is Vishnu, and I'm a freshman in the computer science pre-major. Today we'll be talking about process controls and the PID controller. So before we get started, what do you guys know about controls or process or like controllers? If you'd like to share anything. Okay. Well, before we get started on controls, let's talk about process and what that entails. A process is an operation or series of operations that uses that acts on fluid or solid materials, where the materials are converted into something more useful. A process takes in inputs such as raw materials, labor, money, and turns them into outputs such as information, products, services that can be in the most efficient way. But during the process, you also have many, by also going through many external influences, such as errors and things of that nature. Process variable are the values measured and controlled during this sequence. So they are your temperature, velocity, position in the underwater robotics. In our robot case, we measure position and velocity of the robot. And they could be, these variables are measured and corrected during the course of the process to make sure our end product is the best.
Vishnu. There you go. Okay. I just thought you were meant to be on a slide. You're good.
Sorry, that was fun. So where's process used? So processes are used generally in industry. And so in the process industry, you take raw materials, as I said, and make them into more useful things. And it could be like in your kitchen when you're making food. When like if you're making your salad, you want like you want like I'm not a huge salad guy, but you have your lettuce, and you can have tomatoes or spinach and all these other types of things, and you put them together, and you're like, okay, what kind of ranch do I want? How sweet how sweet should it be? What's the salt content? And these types of things you're measuring, those would be your process variables. In industry, there are different process variables as I discussed previously, whereas they control temperature, velocity, and like things of that nature that really affect or really in making the product. For example, in paint making, you have the raw materials such as solvents, oils, resins, and tints. And those are raw materials you put into the metering deck, and they get dispersed. There's 4 different colors here, and so there's 4 different tubes. The pigments, obviously the different colored pigments that you want to use onto the paint. Then they go into a premix tank and get put into a dilution container, where you could have a process variable such as the viscosity or the solute-solvent ratio of the paint. And then it goes into the filling machines, it gets filled in the containers, sent out to the vendor and eventually the customer. Discrete manufacturing, on the other hand, also uses controls. So both of these process and discrete both use controls. Discrete manufacturing is where you take already created products and assemble them. Controls in this case would be precision of assembling. Also, you might have heard the term tolerance. So there's like certain tolerances that you had to fit in those are the measures of precision that you have to fit in the product. So such as here, you have these people in the bottom left or bottom right, you have these people building Samsung phones, I think they're Samsung phones, and they are assembling the product, and there's a tolerance to it so that it has a perfect fit. And each also had to make sure each product is built similarly, so that there's no like discrepancy between to show uniformity. So what? And now we're going to go to controls. What are controls? Controls are methods to force parameters in an environment to have specific values. So when you're controlling something, you'd want to, let's say you're launching a missile, and you're on a plane, you're on like a fighter jet, and there's like another fighter jet, the enemy fighter jet, and you have your missiles aimed at that plane, and that plane is moving around because you're trying to dodge. You don't want to get hit. You're probably gonna die, right? So then the GPS, the GPS system on the missile can correct for that and see where like what position do you have to be at to attack the plane in front of you. And if you've seen those old times World War II movies, a lot of times they want to get right behind the plane or right under, so that they can like fire up or like fire straight at the back of it and blow it up. In process controls, the main objective is to regulate the value of the process variable. So yeah, again, these could be things like temperature, cost, viscosity, position, velocity, things like that. Control loops. A control loops is where a control is done. So control loops is, as you can see in this diagram, really has four major parts. It has the disturbance, measurements, set point, and adjustment. So first, there's some sort of disturbance, and then you take measurements of the process variable. You take measured process variable and compare it with the set point. The set point is your desired value. Your measurement, your process variable, is your actual value. So you compare the two, you come up with an error, and you make adjustments on the error and repeat the process so that you have until you have the least amount of error possible. Generally, there's two types of loops. There's the open loop and the closed loop. And we're going to discuss that. So open loops, they are just in and out type things. So like your light bulb on and off, lights in any fashion just on and off, unless you have those smart lights where you leave the room and they turn off by themselves, where normally you just turn them off, right? And they could be your electric hand dryers. You put your hand in, the hand dryer turns on, and it's like, and then you put your hand out, and you take your hands off, and it doesn't. It just stops blowing out air. Also, you could have like your washing machines. Your washing machine keeps rolling, and obviously there's set time for it, and it just keeps doing what it has to do. Like, it's not going to stop when it's like, okay, yeah, like I understand these clothes aren't washed enough. I need to go back and rewash them. No, like it just does. When open loop systems first start, they usually don't stop until they finish, and they don't have necessarily feedback control. So if there's errors of any sort that you might consider errors, they cannot fix them. So take this example of, let's call this robot Wally. And so Wally has a task to get himself over to at least past the red border. Now, in this task, Wally has, as long as Wally's functioning, he has good motion. Wally can move in any direction, whether like I don't know, like his traction going backwards instead of forwards or something, and you miscalculated his velocity, things of that nature. Wally is going to get to the red border in this task. And this is the example of a open loop where you first start and you end, you don't have any corrections. You have no scope to make corrections, but it's used in areas where you don't need to make corrections. Similarly, in this example, if you're telling Wally to go from position A to position X, with say the same sort of like hindrances as a miscalculated velocity, or his tracks are like going the other direction, or there's something like dirt in his track, so he's one of the tracks isn't working or something like that, and the angle is different. The open loop system does not correct for where Wally's supposed to go to. So Wally could start off here and have to be going straight, but he just goes in another direction and ends up where he's not supposed to go. So in things where accuracy is important, open loop system isn't really the best system to use. A better system would be a closed loop. Now, the closed loop has the same functions of an open loop, where it has the input and an output, but it has a extra function that's in the feedback control. Now, the feedback control basically takes the output, what you get, loops that back into the input to be evaluated, and it calculates an error, and then plugs it back, makes adjustments and plugs it back into the input, so that you have less error and get where you're actually supposed to go to. So in this case, Wally would have output, and let's say he would move like 1 meter, and let's say the angle is wrong. It would sense that and say, okay, Wally, you are not going where you're supposed to be going. You went X degrees this way. Let's try to go in a slightly the opposite direction, so that we can get you at least on somewhat of a like zigzag your way to the end goal. So it won't always be pretty, but when you're doing feedback control, you have the feedback of the errors that you're getting and have the ability to fix them, whereas in the open loop system, you don't have that opportunity. Closed loops can also be again, things like missile launchers, thermostat. When you're trying to control the temperature in your house, and let's say you wanted to keep it at 70 degrees, but sometimes the it's like 80, let's say it's like 85 degrees outside, and so inside, so and let's say it's 85 degrees inside. Then you would turn on some sort of you would turn on the AC, so that you bring the temperature in the house down to about 70. Or let's say if it's like 25 degrees inside, then you turn on the heat, so that you get back up to that 70 degrees. A really good example for this though is a cruise control in cars. So cruise control generally, basically, you have it follows the steps of a control loop. So you have a disturbance, you have a set point, you have measurements to be made, and it makes adjustments. So first you have a let's say you're going normal on a flat road, and you have your cruise control set, and it's going fine. Well, now eventually, let's say you come up on a hilly road. On a hilly road, obviously in a hilly road, to keep the same speed, because of that constant error of the gravity pulling you down, you have to keep cranking the valves a little faster. That's that's the job of the engine. So the engine calculates the voltage proportional to the speed of the shaft. Then the voltage is subtracted from the desired voltage to determine the error, which gives information about the desired speed versus actual speed. So let's say you're going your desired speed is 65 miles per hour, but you come on the hill and using the same number of cranks to go 65 miles per hour, let's say it brings you down like 5 miles per hour. So you go in 60. So then the voltage calculate the engine would calculate this and say, okay, we need to crank a little faster, and regulate the throttle, which the throttle would be the process variable in this case. Is it has to be either you have to keep pushing on it to either crank faster or you ease off. So you don't have to go ease off to slow down, and you keep cranking the throttle so that you're able to go a little faster and keep the same velocity on uphill. Yeah. Next, what does controls have? What does controllers have to do with this? So controller, it takes in the error signal, converts it into use that the plant will understand, and plugs it back in as input. So controller's job is to reduce error in a system. So here we have our underwater robotics robot, Puddles, and Puddles is built-in software. It has a PP controller, not a PID controller. We'll get to that, which helps it, regulate the position and velocity and get to where it needs to go to with minimal error. So today we'll be talking about PID, which is a proportional integral derivative. Those are the three modes used by the controller to calculate error and input it into the system. This diagram on the right corner, bottom right corner, is the constants that are going to be multiplied with the three modes of use the three modes to generate how much error or how much each mode matters. Like, so your weightage in grades. So like your tests are worth like 50% and like your quizzes are worth like 10% sort of thing. First, proportional. So proportional is error correction. So proportional controller is always trying to get the error to 0. So proportional reduces sudden error. It keeps the system stable, and it has some disadvantages. Like in the process of closing the error as fast as it possibly can, it sometimes goes past where it's supposed to go and creates a new error where it then, tries to cover that error as fast as it can and goes a little bit like past on the other direction and then keeps oscillating. So sometimes proportional can do that, but it is used to close the error to 0 as fast as possible. You have the equation to calculate the weightage of it is shown earlier. The Kp, which is the the constant Kp times the error, and that'll give you the weightage of the amount of error, weightage of the amount of the input that you're calculating to plug back in to the plant or the system. And when error is, you can see from the graph, when error is positive, output is positive. And where error is negative, output is negative. Error is 0. Excuse me, sorry. Error is 0, output is 0. Something to showcase this is this Excel document. So here we have a scenario where you're at a red light and you just turned green. You're trying to get from 0 miles per hour to 5 miles per hour to 5 miles per hour. And you have, your air, you have output acceleration, you have your P controller, and the change in time. So if you look here, the error is actually, this is the error. It says output acceleration, but here, if you notice, the output, the error numbers are the same as the output acceleration numbers. For this scenario, as we have P equals 1. The error is directly proportional to the velocity, because as the velocity is getting closer and closer to the desired value, your error is getting smaller and smaller to 0. And same with the output acceleration. Output acceleration is also decreasing to 0. Now, just because the output acceleration is decreasing It doesn't necessarily mean you're not pushing as hard as you can, because you're pushing to get from that 0 to 5 miles per hour. The P controller is pushing to get you from that 0 to 5 miles per hour in the same level as it is in the beginning. However, the output acceleration is actually related to the air, which is related to the velocity. So when, which is also related to the output acceleration. So when you have, as the velocity keeps increasing, your air keeps increasing, and then your output acceleration keeps increasing. As velocity keeps increasing, your air keeps decreasing, and your output acceleration keeps decreasing, and it goes around in a circle with all of them being proportional to each other. Derivative. Derivative measures how fast the air is changing. It's usually used as a dampening force to slow down the rate of output and prevent overshooting the desired value. So, for example, as I talked about earlier, in the P controller, there's a lot of can do a lot of overshooting, and the D controller can stop that from occurring. Now, one of the key things with the D controller is you can't use it by itself, because the D controller just regulates the rate of output. It does not change the constant error. So we are going to have to use the P controller to showcase what the D controller can also do. So just explaining this demo, we have the slider, which is position. Now the blue line is the actual position where it is right now. The gray line is the intended position. This is like this is like an incline, which we'll get to later. And yeah. So in this scenario where we're trying to get the car to go from here, from this side of the world to the other side, you can see how in the beginning it's continuously oscillating or a little bit due to the P controller, yet it slows down to 0. If we were to take the D controller off, the P controller would never stop, because there is no dampening force to tell it that we are getting, so to tell it that we are reaching the error, we are reaching the error is getting smaller and smaller. The rate of output should also be smaller and smaller. So when we keep the KD at, say, 5, and drag it over here, notice how it almost never overshoots where it's supposed to go. Like, right, the blue line is right on there with the gray line, and it's not going past. It will go a little bit past, maybe like a tiny bit, because of these aren't perfect calculations, but it's pretty close to being on the dot. And that's what the D controller does, is when you're getting from point A to point B using the proportional controller, trying as fast as you can to reduce the error of reduce the error of position, KD helps dampen the extra error that can be caused by trying to solve the error, by making sure that when you're coming close to the error becoming 0, slow down the output as well, so you don't go way too far past it. Finally, we'll come to the integral controller. The integral controller is a path used to detect and remove constant error. This constant error can be something like gravity. It could be your contact forces. And an integral calculator can also, it sums up the error and can reset the position of the back to the set point. It's also called the reset controller. You don't really usually use the I controller by itself. You normally you use it with in accordance with the P controller, or you use a PID controller. So if we were to try a P and then a KI here, we could see that and introduce a constant error, which would be this tilt. Notice how even though the car is just dropping, or the car is just sliding down, the KI makes it not slide, keeps pushing it back up. So if we were to get from if our goal was to get move a little further up the incline, we would eventually move further up the incline, even though in the beginning the car would slide down, and that slide down would be calculated by the integral controller, because that constant error, and it would do the opposite and make sure to the distance that you slid down, you would increase, or you would go forward and get rid of that constant error. Now, this oscillates because there is no dampening force like KD. But one of the reasons why the PI controller is used so much is because it gets rid or it solves the error of it solves the constant error, and that's one of the most important errors to solve. So if we were to switch this KD to let's just move this back here, and if we were to make KD like 0.2 or something, we would see immediately, even with a small KD, how if you're moving up, you're not seeing the same level of oscillation, because the KI, while it calculates the constant error, accumulates a constant error through integrals and pushes back up, it doesn't necessarily account for the actual position where we have to get to, and see that, okay, we're here now, we got to stop. It doesn't do that. So and the P controller just bursts through and is trying to solve things as quick as possible, which there's also nothing to slow down the P controller as well. So that's why we need when you plug in the D controller, even a small number of D controller, you get the system to be stable. Another example of the I part is when you are is how the integral works. So you see a lot of times where even with a little bit of I controller, how it just overshoots the where it's supposed to go to. So you can see how it's barely going above the orange line here, which is the desired velocity, even at a small KI. And if you were to add like a KI like 0.2 or something, it would go way over. And that's due to the fact that it's actually has an error in there's an error in accumulating the air. So it accumulates the air even when you're speeding up, not when you're slowing down. So in the beginning, when you're at 10 meters per second squared acceleration, we're accelerating at 10 meters per second squared. What the I controller does is calculates that error as well, and adds that on. So it's extra error that's calculated, which then has to show somewhere above the desired value and goes past the desired value. So a lot of times people choose not to use a PI controller. So now this is also a PI controller, where you have a scenario of you're stopped at the bottom of a hill, light just turned green, and you're trying to get to 10 meters per second. And you have the desired velocity, error, integral output acceleration. You have the PID, and you're trying to find the actual acceleration, which occurs due to the constant air. So now this is normal physics and like normal freshman physics. Could you tell me what inclined plane physics? Could you tell me what equation could go into this cell right here, which to calculate the actual acceleration? The actual acceleration is smaller than the output acceleration due to the constant air. And I'm going to give you a couple minutes to try to figure that out.
Is this sheet available somewhere, or will it be made available?
Okay.
We'll probably just paste it into the chat or something when we're done.
Okay. Yeah, that's probably my bad.
Okay. Well, that's in Teams. I mean, the Zoom chat. But yeah.
Chat.
Well, if you send it to me, I can do it.
That's fine too.
Okay. Sorry. Parth, attach. I don't even know where this is. Gosh. Can't. Wait, no. Is it PID controller? Oh, I guess I could just do it in the chat. That was pretty easy. I didn't realize it was that easy.
You're good.
Sorry, guys.
Yeah, I mean, for the people who are kind of learning this for the first time, do you guys have any like questions up until this point? Because I know a lot just got covered.
Parth, can you send it? Because it kind of didn't work.
Sure, you're gonna have to shoot me the message on Teams.
Oh, I didn't. Shoot.
Oh,
Yeah,
he
okay,
he uploaded it. He just didn't hit the send button. Yeah, I think so.
There's insert. There's not insert.
Okay, there's the sheet.
There you go.
Thank you.
Your scenario would look something like right, and then you would have a car. Sorry, bad drawing.
Oh, it's a pretty good car.
And you have, the lights. Green. And just trying to get the, the output acceleration is just right now output acceleration not just something. So you know the output acceleration if it's normal, and you're just trying to calculate the acceleration in on an inclined plane. So it would be smaller, and you had to figure out what would the equation be. Does everybody see the Excel sheet?
Yeah,
Yep.
we do.
Okay, sorry.
So it'd just be like a constant offset of your acceleration or something like that, right?
Right. So there would be a constant that given the angle, sorry. Okay, so given this angle right here, which would be the angle of incline, which here you have the 5 degrees. Try to figure out what the acceleration here would be, and I'm gonna give you a, I guess can I give you like some sort of hint?
It's your presentation. Do what you want.
Right. So you have mg sine theta.
Ooh, back to physics. Ooh.
And then you have I guess you have mg cosine theta. I kind of gave it away, but that's probably not what I'm supposed to do.
So yeah, you just plug that in then, because that's opposite the force. You're just counteracting the force.
Oh, well, wait, no, hold on. I erased the answer that I gave, so figure it out from there. I don't know. Yeah, it's just basically. But again, somewhere you might have forgotten, because I guess you're like, seniors. We're gonna give it a couple more minutes, and then, I mean, does anybody have it yet? Or I guess I did. Does anybody did get it before I put it on the paper?
Just in the interest of time, let's
Yeah.
Right. So it's just the g sine theta, which is like the force of gravity puts on you when you're on an angle. And so you have here, the output acceleration is the acceleration if you're on like a flat land, right? And when you have no constant air, so when you introduce a constant air like a hill, you have to have the output acceleration minus 9.8, which is gravity, times sine. Times sine of 5 times pi. Pi over 180, because it wants to, I think XL is like a radians. Pi, I believe, like this. Pi divided by 180 gives you the radians. That's it. Yeah, 9.8 times sine of 5 degrees. Enter. Hold on. What is the issue? Right, and that's going to be the actual acceleration of the car in this scenario when it's going up a hill. And what the eye controller does in this case is it accumulates the air and in the integral here, and which is really just it's really just the time times the air. So it's accumulating the air over time, which is the integral of it. And as the integral keeps getting the air integral keeps getting larger and larger, you have your actual acceleration and your actual air getting smaller and smaller, and your velocity reaching the final velocity. Yeah. So in conclusion, PID controllers are used in a lot of places. PID is really an electrical engineering concept. Controls is really an electrical engineering concept, and the closed loop, which is the PID control, which is like it's conceptual. You have like 8 more modes on it, like not just like proportional integral derivative. You can do like a bunch of more math things to it, but it all falls under the umbrella of control loops, and these are some of the things you can do with some of the objects that use a control loop system. Control loops, which is a closed loop system, where you have error feedback, and you have like if it's like just follow the process of measurements, disturbance measurements, set point adjustments, and then you keep repeating until you get to where you need to get to, or you get the value you need to get. So with that being said, thank you so much, and it's been really cool.